In the previous video, I introduced the Write Your Own Tiny Programming Systems course, and I gave you some background on the idea of building tiny programming systems. Now I want to get back to this and say a little bit more about tiny programming systems, both as a research methodology and as an educational tool. So if you look at what academic research is about, it's trying to study some basic essential principles of the nature or human creations and so on. And we're often trying to do that in isolation from other factors to kind of uncover the core of something. And typically this means that you have to ignore a lot because you're kind of focusing on a small particular situation. If you're studying programming, then there's a lot of things that people very often ignore. If you're looking at different programming paradigms, you might not care so much about the efficient implementation of the programming language or the compiler. We are also often ignoring whether a language achieved some widespread use because that's sort of not essential for understanding the concepts of the language. People who work on programming language theories will ignore things like editors because they're not related to the core thing that they're interested in. So there's different methods. A lot of people who work on programming languages will work on programming language theory, where you sort of study the formal semantics of a programming language. And this is great because you can understand the core idea and show that in some sense it's a formally sound concept. But when you're doing this, you're ignoring how the language could be implemented. You don't even have an implementation at all, and you're focusing on sort of small functional language with maybe lambda expressions, but no other practical features. If you're studying programming from the perspective of the human-computer interaction, then you may look at the user interfaces, study how users actually interact with the system, but maybe you don't care so much about the inner working of how the thing actually works, how it's implemented, whether it can be implemented in an efficient, large-scale way. You're sort of interested in how the users work with the system. A lot of programming system research includes some sort of performance evaluation. So when we're building an efficient system, or we want to show that something is efficient or better than some other system that we have, then we will be measuring some performance. But again, this has to typically ignore many aspects. It will ignore whether the system is usable and people will actually use it in a way that leads to the desirable performance. We might also ignore other design implications of the sort of specific thing that we are focusing on. So if you're kind of measuring the performance of a system, you are again ignoring many other practical aspects. So with TinySystems, we are also building something to illustrate sort of core idea in its isolated form, but we are ignoring a lot of things. And in this course, I will be doing exactly that. So what I'm going to be ignoring in the course are things like syntax and writing of parsers. In the course, we will typically not really have any serious syntax. Most of the time, I will have no syntax at all. I'll be just sort of directly constructing data structures that represent the program. And this is one of the things that I'll be happy to ignore. The other thing is I will be ignoring how to compile things or how to make them work on modern runtimes. This is someone else's problem, And in the TinySystems course, we're just interested in the sort of core idea of how the system works. And for that, it's perfectly sufficient to write relatively basic interpreters. The next thing that I will be ignoring is formal semantics and any sort of proofs of correctness. So we will implement something and we will have some tests to show that it works as expected, but I will not be concerned with whether every single detail of this is correct and what are the possible corner cases. We will look at some because very often there's interesting corner cases that you can encounter and explore, but the point of the course is not to sort of write down the formal semantics. We might kind of pick one interesting feature that's maybe not something that you would include in a small formal model, but lets us do something interesting and fun, like printing to a screen or something. And none of the TinySystems that you will build in this course are going to be useful for any real-world uses. We will try to implement sort of enough of the programming system that you can do something that illustrates the programming paradigm or the interaction just enough so that you can see that it could possibly work, but we will never really build anything that's big enough to do real practical programming. So with these limitations, what can we actually study? And there's still a lot of interesting things. We can talk about the interaction with the programming system. We can talk about how the various stateful interactive systems work, which is something that's often ignored in programming language theory. We can look at the core logic of some inner working of a system. So one example, for example, is Prolog, and there's some key component to how that works, how it performs resolution. And that's something that you can kind of implement, taking care both to sort of understand how the overall structure works, but also sort of what are the fine details. And this is a kind of thing that is not really compatible with academic papers. You cannot print that on 12 pages of A4 paper, but a lot of the things we will build will not be significantly longer. So sort of try to explain the core ideas of how different programming languages and systems work using a small-scale implementation. And I want to give you one nice example that illustrates this. And this is based on a project to understand interesting past programming systems. So the programming system that we're looking at here, you can see on the screen, is called Pygmalion. And this was one of the first programming by demonstration systems where you can sort of enact a program and then replay it. So there was no code, it was just interaction, and it also incidentally is interesting as the first programming system that used the concept of an icon, but in a kind of more interesting, richer way than we do today. And this is a system from 1980s whose source code is available as a scanned Smalltalk 72 source code. So it's really, I don't think there's any chance of running it directly very easily. And one of our students at Charles University built a sort of re-implementation of the system that re-implements very accurately how the system behaved but sort of uses somewhat different user interface. So one of the examples from the original paper was implementing a factorial. So I'm going to define a factorial. I'll drag it onto the screen here, and I will take a number 5, put it in here, and now we can try running factorial of 5. Now, of course, we haven't defined factorial, so we just get sort of inside a new page, new screen, where we have to say how to do a factorial of 5. And to do that, we need to test if 5 is equal to 1. So I'm going to construct the condition here. Evaluate the condition. This is false. And now I need to do branching. So I'll put an if here using false as an argument. And again, I run this. And now we are in the false branch of the if. And we want to calculate factorial. So for that, I need to take the argument, subtract 1. This gives me 4. And I need to do factorial of 4. And again, I will sort of play this. And what happens here is that the computation proceeds for as long as it can, and it continues until it reaches the argument 1, because then we are in the other branch, and we haven't specified what to do if the condition is actually true. So if that's the case, we take 1 and we return that as a result. And then it sort of propagates back until it gets to the next state where we haven't said what to do. So that was when computing factorial of 2, we now have factorial of 1. And what I need to do is to multiply the result of this with the argument. This gives me 2, which I then take as my result. And now I replayed enough of a factorial so that I can compute factorials. And factorial of 5 was 120. If I say, give me factorial of 6, now I can just drag the 6 here, run it, and here's the result. So I defined factorial, but I did that without writing any code. I did that without working with any variables. I did it just by manipulating with concrete numbers and the binary operations and the conditional. So this is an interesting example of a recreation of a programming system that kind of illustrates, captures how the thing really worked. And so that was kind of a research use of a tiny programming systems, where here we were looking at a historical example that had some interesting aspects that we're trying to recreate. But you can also use TinySystems to imagine new paradigms or sort of uncover how exactly the interaction with the system worked. The Pygmalion project was an interesting example because you can't really experience the interactivity just by reading a paper. So there, being able to play with it is really an eye-opening experience. And in the course, we will sort of mainly be using tiny programming systems for educational purposes. And I think one of the arguments here is that the best way to learn something is to write it on your own. So if you write your own implementation of Prolog or ML type inference, you will have to understand the overall structure, the key principles, but also some of the important subtle details. And Programming is of course fun, so you will learn these fairly sort of general abstract concepts in a hopefully engaging way, and I will also try to show you that even by implementing a relatively small version of a programming system, you can actually do enough to have some fun and run things that you maybe wouldn't expect that it will work with just a few lines of code. The idea of using TinySystems for teaching is not something new. There was a book called Programming Languages and Interpreter-Based Approach that actually did something like this in the 1990s. It was using Pascal as the implementation language, and it looked at some of the languages that we will be looking at, like Prolog, and also many other languages that the history has now somewhat forgotten. I think some of the focus of this book has been on things like parsing, which is something that I think is not as essential, and I'm going to be ignoring that. But even in the world of programming languages, there are really interesting sort of related projects. There was also an interesting collection of tiny implementations of AI systems in the 80s called Inside Computer Understanding. And what this was doing is that it was kind of trying to re-implement some of the pioneering symbolic AI programming systems, symbolic AI systems that in a way that can be understood, can be kind of conveyed through sort of small enough amount of source code that it can be printed and discussed in a book. So one last reference that I think illustrates the kind of value of this approach is the online journal called Distill, which has been publishing for 5 years small interactive explanations of core machine learning algorithms, again, including a tiny implementation that actually worked in the web browser. So those are all interactive articles that you can play with online. And in an analysis of the medium, the authors of the journal explain some of the things that you get by having these small interactive systems. In their case, it was about machine learning. In our case, it's about programming systems. And it includes things like makes the systems playful. You can actually sort of explore and see how exactly it behaves, what are the limits, and so on. It prompts self-reflection, so you have to sort of think about what exactly is happening when you're exploring one of these systems. And having this available in a sort of interactive environment reduces cognitive load in that you don't have to kind of manipulate abstract symbols in your brain. You can actually run it and see what happens. So that's some of the background and some of the motivations for this course.